You know, every single day, whether you're on your phone or your laptop, you're being protected by an invisible shield. It's this incredibly complex fortress of digital defenses that stands between you and all sorts of cyber threats, a lot of which are way older than you might think. So today, we're going to pull back the curtain on one of the oldest attacks in the book and the absolutely brilliant defenses that were built to stop it.
So here's a question for you. How does your phone, this super modern piece of tech, defend against an attack that hackers have been using for decades? I mean, we're talking about a trick that's practically ancient in computer years. Well, the answer lies in this silent, multi-layered battle that's happening deep inside your computer's memory right now.
All right, so the attack we're talking about is called a buffer overflow. It's a classic, really. It's one of the foundational techniques for breaking into computer systems. And to really get a handle on the defenses, we first have to understand the attack itself. Okay, imagine a program has a mailbox. That's the buffer. And it's designed to hold a letter of a very specific size. A buffer overflow is basically like someone stuffing a ridiculously long letter into that tiny mailbox. It's so long that it doesn't just fill the box, it spills out and starts piling up in the mailbox next door, totally overwriting whatever was in there. And if the attacker's clever, that spilled over part isn't just random garbage, nope, it's a secret, malicious message, code that they want your system to run.
So let's think of your computer's memory like a digital fortress. A buffer overflow is just the attacker's way of trying to smash through its walls. So how does this fortress fight back? Well, the very first strategy is to be completely and utterly unpredictable.
The first and maybe most fundamental defense is to just hide the floor plan. I mean, think about it. If an attacker has no idea where the throne room or the treasure vault is, it makes it a whole lot harder to plan a successful attack, right?
This amazing defense is called Address Space Layout Randomization, or ASLR for short. Without it, the fortress layout is totally fixed. Every room is always in the exact same place. An attacker could study the blueprints for days and know exactly where to strike. But with ASLR, oh man, every single time the program starts, the entire fortress is shuffled. The main gate, the barracks, the library, they're all in new, random spots. It's like blindfolding the attacker before they even start. And this isn't just about moving one or two things around. This randomization applies to all the key areas of the fortress. ASLR shuffles the location of the stack, where all the temporary data lives, and the shared libraries, which are kind of like the castle's toolbox. And when you combine it with another technique called PIE, that's Position-Independent Executables, it can even randomize the location of the program's main code. The whole thing becomes a moving target. And hey, this isn't just some abstract theory. In an operating system like Linux, you can actually control how much randomization you want. You can set it to 0, which basically means the fortress blueprints are public, no randomization at all. Or you can crank it up to 2, which is the default on most modern systems, and it shuffles pretty much everything. It creates this incredibly unpredictable environment for any attacker. But what if an attacker gets lucky? I mean, what if they guess the right location and actually manage to sneak their malicious code inside? Well, that brings us to the next powerful layer of defense. This is where something called Data Execution Prevention, or DEP, comes into play. Think of it like this. The fortress has a rule that certain areas, like the kitchen or the library, are read-only zones. You can go into the library and read all the books you want, but you are not allowed to issue new royal decrees from in there. DEP does the same thing. It marks areas of memory that are only meant for data, like the stack, as non-executable. So even if an attacker manages to write their malicious code there, the processor just flat-out refuses to run it. Simple as that. And just like inspecting a real fortress, engineers have tools to check the walls. They can use a command line tool called readelf to look at different sections of their program's memory and see if they're properly protected. So when they run this tool, they're looking for these little flags. If they see RW, that means the area can be read from and written to, which is totally normal for data. That's a secure wall. But if they see RWE, read, write, and execute, that is a massive vulnerability. It's a giant, flashing neon sign that an attacker could not only write malicious code there, but could also trick the system into running it. Making sure data areas are never marked as executable is absolutely crucial.
All right, so our fortress is getting pretty secure. The layout's hidden, and some areas are basically locked down. But there is another incredibly clever defense, a hidden trap, and it's named after a very, very old warning system.
You've probably heard the phrase, a canary in a coal mine. For centuries, miners would literally bring a canary down into the mines with them. If dangerous, odorless gases were building up, the poor little canary would collapse first. It was an early warning system that gave the miners time to escape. Well, the digital version works on the exact same principle. It's a silent detector for a hidden threat.
So here's how it works. When a function in your program starts, the system places a secret random number, our canary, on the stack, and it puts it right next to a supercritical piece of info called the return address. Think of this like posting a guard right outside the king's chambers. Then, the program just does its thing. But right before it finishes, it goes back and checks on that guard. If the canary's value has been changed, it means a buffer overflow happened. The program instantly knows something is wrong, sounds the alarm, and shuts itself down safely, stopping the attack before any real damage is done. Pretty clever, right?
So, we've got randomization, we've got non-executable zones, we've got these little tripwire canaries, but the real key to modern security isn't just one of these things. It's all of them working together, layered on top of each other.
And there's even one more defense we can throw in the mix. It's called RELRO. What this technique does is lock down the fortress's internal address directory after the program starts up. Imagine an intruder trying to change the signs in the castle to send the guards to the wrong location. RELRO stops that by making those internal address tables read-only. It's like welding the castle directory shut so nobody can mess with it.
This whole thing perfectly illustrates the modern security philosophy of defense in depth. See, no single defense is perfect on its own, but when you layer them all together, they create a seriously formidable fortress. ASLR hides the layout, DP makes key areas non-executable, stack canaries act as tripwires, and RELRO protects the internal maps. An attacker has to find a way to defeat not just one, but all of these mechanisms to have any chance of succeeding.
These protections, all developed over decades, are what form that invisible shield protecting you every day. But here's the thing about cybersecurity. It is a constant arms race. For every brilliant new wall the defenders build, the attackers are already hard at work figuring out a new way to climb it. The siege is never really over, which it leaves us with one final thought. What will the defenses of the next digital fortress look like?